Good afternoon, everyone. My name is Sarah and I am the current chair of the SRP Webinar Working Group, and I'd like to welcome you today to another one of our lunchtime lectures in partnership with AURPO. Today's topic is the key role of Cobalt 60 in today's world. As always, I've got a couple of things that I need to mention just before we start. We will be recording this webinar and adding it to our YouTube channel, so you can check it out there if you would like to watch it again. You can obviously ask any questions through the Q&A box and like any that have been asked by somebody else. At the end of the talk today, we'll ask as many as we have time for, starting with the most liked ones first. And any that we don't have time to ask will be emailed to the presenter afterwards, and then we'll pop his answers on our website. There is the code for registering your CPD points, so don't miss out on that. We'll pop that code and the email address that you need to send it to into the chat, so you can note that down at some point during the talk. And as always, please send us any feedback. We want to know what we're doing well, what we can maybe improve on, and any topics that you'd like to see in the future. Whilst you're here, if you're not already a member, then I'd like to remind you just of the benefits that you could be getting if you were a member. All the information about benefits and how to join are available on our website. Also, we have got issue 8 of our magazine out. If you've not read that, then I highly recommend that you go take a look. It's got some really, really interesting articles in it. And then finally, I'm sure you've all got ERPA 2026 in your calendars. If not, it's the 1st to the 5th of June 2026 in Liverpool. Planning is underway and we're all really looking forward to it, so hopefully we will see you there. So without further ado, I'm going to hand over to Ralph, who is going to introduce our speaker for today.
Hi, thanks, Sarah. Just before I introduce Riccardo, I want to mention quickly the AURPO Society. It's an organisation for anyone involved in radiation safety in universities, research or teaching. You can find out more on our website at www.aurpo.org.uk. Our next annual conference will be held in Glasgow on the 22nd and 23rd of September 2026. Riccardo is a nuclear physicist with a PhD from Uppsala University, where he focused on neutron data for Generation 4 nuclear reactors. He has held research positions at the European Commission and the European Spallation Source, and now leads global radiation safety initiatives at Elekta, based in Stockholm. His career bridges nuclear research, radiation protection, and medical physics, the field that first drew his interest as a student in Italy. Outside of his work, he writes popular science articles on physics and radiation, and is a father and stepfather. Riccardo, over to you.
Hello, everyone. And I will share my slides and we will talk about Cobalt 60. And it's really exciting to see so many people joining for a webinar where we talk about one single isotope for almost an hour. How exciting can be that? And I hope it's going to be exciting, and I will do my best to keep it interesting for you. And here is a little bit of the outline of this presentation. So we'll talk first of all a little bit about Cobalt. We need to introduce the main character of the story, and then we will see specifically Cobalt 60, what is the birth of Cobalt 60, what is by far the main application of Cobalt 60, maybe you already know that, but then we'll look at some less known applications, and I will conclude this presentation talking about the one that is my favorite application of Cobalt 60. And then it'll be interesting to see in the questions, maybe some comments on which one is your favorite application of Cobalt 60. So first of all, what is Cobalt? Well, Cobalt is a chemical element, so far so good, and we found it in the Earth crust, and it naturally occurs in various minerals, and in fact, it's not possible to find cobalt as in its pure metallic form in nature. And 98% of cobalt, this is a little bit surprising sometimes, is in fact produced as a byproduct of large-scale copper and nickel mining operations. So there is no such thing as cobalt mines, except for some small mines in Morocco and in Canada. But most of the time, you're mining out copper and nickel, and then you get cobalt as a byproduct. And here is a tip for a question to ask me at the end of the webinar. You can ask me, okay, cobalt is a byproduct of mining of other elements. Why do you say here that also Cobalt 60 is a byproduct of something else? Let's see if someone dare to ask it. Meanwhile, I wanted to show you some actual Cobalt pictures. If you Google it or search on or ask to ChatGPT, you get some shiny silverish cube. But in fact, the way you find Cobalt in nature looks more like these three images. But if I say Cobalt, then it will be very interesting for me to ask you what is the first thing that pops to your mind. And I guess every one of us have an answer, but there is only one correct answer, and the answer is batteries. Cobalt is batteries in our world. In fact, battery applications represented like 76% of the total demand of cobalt around the world. These are 2024 data. And batteries represented 94% of the year demand growth. So it's a big market for batteries. 43% of the cobalt that is mined annually ends up in electric cars. The remaining part, 30%, go into portable electronics, computers and telephone mostly. The largest non-battery application for cobalt is superalloys. If you look at the data on how much cobalt has been mined globally over the most recent years, you will see that the demand and the mining is skyrocketing. 254 metric tons of cobalt were mined in 2024, and this number is projected to increase more and more through the years. And this is driven by battery demands. And just to give you a little bit of proportions, and then to introduce one of the applications that we'll talk about, in one electric car, you have around 14 kilograms of cobalt. And in the telephone that you have in your pocket, something around 5 to 10 grams, depending on the model of your telephone. And a portable computer has around 50 grams of cobalt and powers the battery for just a few hours. In a gamma knife, which is a brain radiosurgery device that I will talk about towards the end of this presentation, you have around 20 grams of cobalt, and that 20 grams are enough to power it for 5 years or more of brain radiosurgery. Now, I see someone raising hands. Well, I don't see it, but imagine and saying, well, wait, so something is cobalt and something is cobalt-60. Well, chemically is the same, different isotope, but you're right. Let's talk about cobalt-60. So how about cobalt-60? The story of cobalt-60 starts maybe with Marie Curie, and I mention her because you cannot give a scientific talk without mentioning Marie Curie, or with Enrico Fermi, and I mention him because being Italian and a physicist, I cannot not mention Enrico Fermi. But in fact, everything started with Lorentz, who invented the cyclotron in 1930s, for which he received a Nobel Prize in 1939. And he was based at the University of California, and he needed a place where to put the cyclotrons, and the university gave him this small building, looks like a townhouse made of wood. And he installed there the first 27-inch chamber cyclotron, and then later on a larger 37-inch, and then larger and larger when he needed another place. But when you read on publications about the Berkeley Radiation Laboratory, one might imagine by nowadays standards some big building. In fact, it was this little house. It's, I think, interesting to see where cobalt was born. And in fact, using the 37-inch cyclotron, physicists Seaborg and Leeuwenhoek, they start producing a lot of different isotopes. They produced iodine 131, iron 55, iron 59, and so on, until 1938, when they did produce for the first time ever in the world cobalt-60. And later, Seaborg, together with another physicist, Macmillan, they even discovered plutonium, but with a larger cyclotron. They couldn't do it with the 37-inch cyclotron. Seaborg, in fact, is credited to have discovered a lot of different elements, americium, curium, berkelium, even one that is named after him, Seaborgium. I hope I pronounce it correctly. And eventually, Seaborg and Macmillan shared the Nobel Prize in chemistry in 1951. Sadly, no Nobel Prize for John Leeuwenhoek, who nevertheless lived a long and successful, happy life, and he wrote a very, very nice book on the physics of cyclotrons, and highly recommend to read it if you need to give a course on cyclotrons. If you want to know more about the birth of Cobalt-60, a good place to go is the website of the Oak Ridge Associated Universities Museum of Radiation Radioactivity. And there they had a lot of materials. There are a lot of funny things, but there are also a lot of materials which were actually donated by Seaborg, including the original activated samples that they used with the 37-inch cyclotron. And there are a lot of stories and first-person accounts of Seaborg on how they discovered Cobalt-60. So good place to go, either virtually on the website or visiting the actual museum. But then from this birth of Cobalt-60, we enter in what is the Cobalt-60 era. And this happened when nuclear reactors, in the beginning research nuclear reactors, made possible, starting from the 50s, to produce Cobalt-60 on a large scale. And this led to the production of the first construction of the first high-intensity Cobalt-60 radiation therapy unit. And this was done by physicist Jones and by Sylvia Fedoruk. She's a super interesting woman with a super interesting life. She's been a politician for some time, a very experienced physicist. I really invite you to go to explore a bit more about her life and her activities. And they built this first unit with Cobalt-60, which they had the idea to call the atom bomb, or the atom bomb that saved lives, maybe an unfortunate name, but so it is. And we started the use of Cobalt-60 in teletherapy machines, which in fact are still used, especially in low and medium income countries. However, with time, the prevalent application of Cobalt-60 was not anymore radiation therapy, but it became sterilization. In particular, sterilization of single-use medical devices. And again, a little reminder for a question at the end. You can ask me, how do we produce Cobalt-60 today? I will not tell you unless someone is asking me. So, sterilization. Sterilization is really the major application of use of Cobalt-60 today in the world. Only in the United States, just in the United States, 16 billion single-use medical devices are sterilized every year with Cobalt-60. And a number comprised between 30 to 40% of all single-use medical devices globally are sterilized with Cobalt-60. I like to say that Cobalt-60 is the single isotope that most contributes to global healthcare. And I would like someone to challenge this, but if you think about 30 to 40% of all single-use medical devices sterilized with it, I think we have a reasonable suspicion that Cobalt could be the isotope that contributes the most to global healthcare. And this irradiation is done in around 200 large irradiation facilities, which are distributed all around the world. And one can go on the website of IAEA and actually find the map and to see where the nearest irradiation facility is located. And in these facilities, they have something around 500 megacurie of Cobalt-60 at any time used for irradiation. So next time you hear the name Cobalt or Cobalt-60, yes, think Cobalt batteries, but in fact, even more having a larger implication is sterilization, and we cannot imagine a world without sterilization. However, Cobalt-60 is not used only to irradiate medical devices. It's used also to irradiate stents, human tissue grafts, but also food to reduce infection risk in patients with an immunocompromised system. Cobalt-60 irradiation is also used for food preservation. Irradiation prevents sprouting, delays ripening, destroys pathogens, and in fact, Cobalt-60 is part of the technologies that the IAEA includes in the technologies that help fighting hunger. And there is a beautiful report. Here there is the Director General of IAEA down there in the corner indicating the report, the atoms for food. And this is the QR code if you want to download it. Or if you don't trust my QR code, you can always just Google it. Atoms for Food is a very interesting report, and they describe all the nuclear technologies, and Cobalt-60 is one of the prominent ones that are used to fight hunger and to provide food to the planet. But now, if sterilization may be something you heard about, I would like to go a little bit more into some more unusual, maybe, applications of Cobalt-60. Maybe you already read about some of them. Hopefully, you didn't read about all of them, so you will get out of this seminar with something new. So we will see how Cobalt-60 is helping fighting the Zika virus and other dangerous viruses and pathogens. We will see how Cobalt-60 is helping bees to produce honey and to stay healthy. We will talk about a process that is called monsooning of coffee beans. Very interesting process, and Cobalt-60 has a part in that. Then we'll talk about, we move from coffee to space, and we'll talk about how Cobalt-60 is helping us to land spacecrafts. And finally, we will talk about how Cobalt-60 is helping us to perform brain surgery. So viruses, bees, coffee, spacecraft, and brain surgery. So let's start. And we start from this technique, which is called the sterile inset technique. Sterile inset technique is a method that helps preventing spread of viruses like the Zika virus, West Nile, or the dengue viruses. And they do that by providing a safe, effective solution that doesn't have any repercussion on the environment. It's 100% eco-friendly, poses zero risk to the environment and zero risk to public health. And the reason is why it's so effective is that the sterilized insects, like Cobalt-60, I will show the next slide, can't reproduce. And by doing so, you prevent any lasting establishment of their population. So it's a natural birth control, a birth control for insects, if you want. And I borrowed this slide from the IAEA. But there is a lot of material on the IAEA website about the sterile insect technique. But essentially what you do is that, first of all, you grow insects in specialized facilities of the species of interest. And then the next thing that you do, you separate male and female insects. Now, female, I'm not really sure what we do with them. I suspect nothing good. But the male insects, they are irradiated with Cobalt-60 so that they become sterile. When they take the sterile male insects and they release them into the environment, what happens is that these male sterile insects will compete with the wild males and will compete for the sexual favor of the female insects. Now, this is a little bit of a red light topic. I hope no children are listening. But essentially, you are having sterile insects sterilized by Cobalt-60 competing with the wild males. And this, as a result, have that the eggs that are laid by the female insects will bear no offspring because are not fertilized. That's pretty intelligent method, I would say, to do that. And in fact, is widely used. It's widely used both to fight spread of viruses, but also to control the population of certain insects that otherwise would risk to affect the environment. But you can use Cobalt-60 also to help insects without necessarily making them sterile. And this is what you do with bees and with beehives disinfection. Now, I took a paper as an example There are some other studies that discuss about this. In this case, in this paper, we have been discussing a specific spores. I don't know if I pronounced it correctly. Is a Penibacillus larvae, and this is an infection that affects the ability of the bees to reproduce and eventually will kill the bee colony. So irradiation with Cobalt-60 is done not to the insects, but in fact on the contaminated combs. And the parameter that is important here in terms of dose is called D10. And this is the decimal reduction dose. So essentially it's the dose that is required to reduce the viable population of the microorganism by 90%. So one measure experimentally the D10 and then deliver a dose so that you kill a fraction that is enough to free the honeycombs of the larvae that is infesting them. And in laboratory conditions, just to give you some idea of the doses, the D10 for isolated spores is around 500 gray, but when you irradiate a full in situ, when you irradiate a full comb, then you need to give higher doses of the order of 2000 gray. What is interesting is that after the irradiation, the combs were placed back into the hives and they didn't show any recurrence of the infection, but also it was proven that the bees start using the comb again. So allowed reuse. The bees were unaffected by this process. And the reason to use Cobalt-60 is that, first of all, the intensity of the gamma emitted by Cobalt-60, a little bit more than 1 MeV, and they have deep penetration that allows to go through the wax and through the comb and to reach the desired dose delivery. It also allows an in situ treatment, irradiation, because you do not need, in principle, to take the honeycombs to a dedicated irradiation facility. You can transport the cobalt on site and do the irradiation on site. And again, high doses inactivate the spores, but it's proven that they leave the comb structure intact, which is pretty amazing. Where other methods that involve heat of chemicals or use of ozone or ethylene oxide might degrade the wax and may result in an unusable honeycomb later on. And there are several articles, but I also found some interesting blogs. I wanted just to put this as an example, like gamma irradiation for beekeepers. Super interesting to read what people can do with Cobalt-60 that usually as physicists don't think about. But let's talk about another very interesting application, at least for me as an Italian and a Swedish, because I like coffee. And this is coffee monsooning. Now the question is, what the hell is coffee monsooning? Well, back in 18th century, when coffee was transported by the British East India Company all the way from India to Europe, maybe to London or to my hometown, Trieste, the travel lasted like 6 months or more, and the coffee beans, they were exposed to humid monsoon weather, salty water, and this resulted in the beans to really be moist and exposed to salty water, monsoons, and to other atmospheric agents for all the way through the journey. As a result, the coffee beans were swallowing and we were changing color, but we also were changing acidity. We have less acidity and we're having a smoother and heavier taste. And if you wonder why I put the picture on the right, is because it happens to be that the guy there on the right, Captain Christopher Berwick, was the grandfather of my grandmother, and he was in fact the ship captain carrying coffee from India to Trieste. But then my great grandfather got out of business and saw the use of sailing ships, and new modern ships made of steel made the journeys much shorter and the beans not being any more exposed to monsoon weather and to salty water. Nice? Well, maybe not, because then the coffee doesn't taste anymore as good as it was tasting before. So they developed this method, which is called monsooning. It is a method where the coffee beans are on purpose exposed to monsoon winds in open warehouses. Some pictures here from the Barista magazine. And then, after several weeks of this exposure, they are transported in the steel ships to Europe. So we recreate on purpose the process. And now we will ask, okay, but how about Cobalt 60? Well, in fact, someone had the idea to try to irradiate the coffee beans. And the main reason to start this process of irradiation was that during the monsooning process, when you have naturally moist environment, you have development of bacterial, fungi, and this can influence the moisture exchange, but also can be a health issue. So we said, let's irradiate monsooning coffee with Cobalt 60 to try to kill the fungal population. What is interesting, reading this paper, is that they actually found that when irradiating coffee during the monsooning process with Cobalt 60, you also have an acceleration of the process. Now you can reach the same level of monsooning in 2 weeks instead of 5. Now, if you ask me why, well, the paper says they don't know yet. And so if you're looking for a side project, something you want to spend your time researching on, definitely coffee irradiation is something for you. And I have it in my bucket list for my retirement. But moving away from coffee, there is some other incredible application of Cobalt 60. And I don't know if you've ever seen the Soyuz landing. And this is a picture from that image, but maybe you don't know that the Soyuz lands thanks to the Cobalt 60. In fact, when the Soviets sent Yuri Gagarin to the space, first man to the space, they have a very good idea on how to send him up. They had no clue how to take him down. So the solution that they came about was to eject him from the capsule at around 11 kilometers up in the sky, and then to have him descend with a parachute. So Yuri Gagarin actually was parachuted back on Earth. But then they start thinking, okay, now we want to develop a spacecraft, what became the Soyuz, that can carry more cosmonauts. And Soyuz still nowadays carries 3 cosmonauts. And it was not possible anymore to develop a mechanism where you eject 3 cosmonauts at the right altitude at the same time. So they said, okay, how do we soft land this 3 tons capsule in free fall from the sky? Of course, with a parachute, but it's not enough. It's not enough. It still arrives too fast. So you need to have some braking engines, some backfiring engines. The problem is that the backfiring engines needs to turn on at a very specific, precise moment, which is 70 centimeters from the ground. Now, imagine the problem. We are in the 60s. We have a 3 tons capsule falling from the sky, arriving very fast despite the parachute. And they need to know when they are at exactly the point of 70 centimeters from the ground, so that the engines can go on in that very moment. And there was no altimeter capable of this. So the idea is that, okay, we take a radioactive source, Cobalt 60, almost monoenergetic, very reliable, 100% uptime, very precise. They put it in an instrument which is called the Cactus. You can Google this, it's very interesting to see the design. And essentially, this was measuring the time of flight of the backscatter photons from Cobalt 60, and by so determining exactly the altitude at every moment in the last phase of the landing, so that they could activate the engines when was the right moment. Which pretty cool, if you ask to me. And in fact, you can see happy astronauts and happy cosmonauts. And if you look for pictures of the Soyuz capsule, you will notice on the bottom of the capsule, in fact, the trifoil, and that is the place where the Cobalt 60 source is installed. And that is the cactus system. Super interesting. There is a drawback though, and this is what they call the Soyuz effect. Now, they installed, not too long time ago, a very nice instrument of the International Space Station, the NICER telescope. I don't know if it was one which was called the NICE, and this one is NICER, not sure, but essentially this stands the acronym for Neutron Star Interior Composition Explorer. So this is an X-ray telescope, okay? It's an X-ray telescope that is placed on the International Space Station to study emission from neutron stars. And this detector is made by an array of 56 silicon drift detector, sensitive to relatively low energies, soft X-ray, but is very, very sensitive to transient events near the International Space Station. And guess what is the transient effect? When the Soyuz arrives or leaves the International Space Station, because the NICER telescope picks up the signal from the Cobalt 60. So there are some papers discussed in this, and I think it's very interesting because in the beginning we were trying to understand what are all the noises that we can see on in the signal from this NICER telescope, and there are many different sources of background, but one is the Cobalt 60 from the Soyuz. So when people ask me, okay, Riccardo, you always talk about Cobalt 60, you like Cobalt 60, you say also there's a lot of nice things about it, sterilization, coffee, bees, brain surgery, I will come to that. Is there anything bad with Cobalt 60? I always say yes. There is one very bad thing with Cobalt 60 is that it is disturbing the signal of the NICER telescope on the International Space Station. And I couldn't resist to show you this beautiful picture, which was taken in January this year of during the service of the NICER telescope by an astronaut, American astronaut. And yes, but now the question is, okay, I've been talking about space, astronauts, but what do a neurosurgeon and an astronaut, or what do neurosurgery and rocket science have in common? Well, you know the title of the talk, no surprise, Cobalt 60. And the tool that I want to talk about is called the Gamma Knife. The Gamma Knife is a stereotactic radiosurgery device, and it's a technology that essentially allows non-invasive brain surgery, and it does it using a three-dimensional array of focused radiation beams, and this is used to treat both brain tumors but also other neurological conditions without surgery. And it's powered, the system, by an array of 192 cobalt sources, and all the sources are focused in one point at the isocenter. And one would ask, okay, but why Cobalt 60 again? Well, it is a combination both of design and intrinsic nuclear physics properties. First of all, the steep dose gradient and the sharp penumbra. Well, imagine this as a geometrical factor. If you want to have a three-dimensional array of gamma rays arriving from different positions, as a three-dimensional array, as I said, it's impossible to do it with a LINAC machine because of space. Instead, you can use radioactive sources, cobalt sources, and distribute them in a way that you can really have the smallest collimator, shortest distance from the sources to the target. And by this, minimizing as much as possible the penumbra area. That means that you minimize the ratio between the dose that you deliver to the area that you want to treat and the dose to the to the areas that you don't want to treat in the brain. Then there is what I call the Archimedes heat ray effect, which, if you want to say it in a more scientific way, is the cumulative dose fall-off effect. Essentially, by concentrating the 192 rays in one single isocenter, one focal point, you, just by doing this, reduce by a factor 1/200, let's say, the dose in the target that you're treating compared to the tissues outside that target. And we are talking about brain surgery, so it's very important to find a way to maintain the dose outside the target as low as possible. But then there is another aspect, which is the dosimetric penumbra. Dosimetric penumbra has to do with the scattering and with the fact that you have a narrow, I say single energy. Of course, we know that cobalt emits two gammas, very close in energy. But essentially, one can treat that as a monoenergetic from any practical point of view. That means that you reduce the scattering and you can control the scatter compared to dose delivery with the system that would deliver on a spectrum. Then there is another fact, it's called the lateral electron equilibrium, and I will show you a couple of slides after this one about it. So, and then I will also talk a little bit about the extracranial dose, because you want to have a system that keep the dose outside the brain also as low as possible. You know that the biological sensitivity of internal organs is higher compared to the one of the brain. So you don't need to minimize you shouldn't minimize only the dose in the brain, but you must do anything possible to minimize also the dose to the most sensitive organs in the person that is treated. So let me talk a little bit about the electron equilibrium effect. So when photons interact with any biological tissue, or any material in general, they generate electrons, okay? Now, the electrons, they travel themselves a certain distance, a certain range in the tissue, and then they deposit their energy. That means that the volume to which you are directing your photons is not the same volume where the energy is deposited. There is a shift due to the range of the electrons. Okay. We say that we reach electron equilibrium when, in a given region, the number of electrons that are generated in that region is equal to the number of electrons that are absorbed. And in that region is where you deliver and so intend to deliver and actually deliver the dose that you want. You say that you have electron disequilibrium when the irradiated volume is too small. It means that essentially the internal volume is too small, so the electron gets out of that volume, and then you have the dose delivered on a larger area. And this results essentially in non-therapeutical dose. So electron disequilibrium, you can think it as a mismatch between the dose that you intend to deliver and the dose that you are actually delivering. And this is critical when you are looking at small targets in very sensitive areas. In fact, this is really a function of the energy of the photons. You need to have enough energy to penetrate, of course. So you say, oh, low energy, I can use visible light. No, not really. X-rays, no, not really. So cobalt have enough energy to penetrate, but it also have just enough energy that you can treat the smallest volume. So the lateral electron equilibrium is in fact a measure of the smallest volume that you can treat. And so if you want to treat really very, very small targets like brain metastasis, or if you want to treat some functional indication in the brain, you really need to have the smallest lateral electron equilibrium possible. And this is why Cobalt-60 is the source of radiation by choice compared to Linacs that produce higher energies and also distributed on a spectrum. And one can see this also in terms of karma. Karma, is the ratio between the essentially is the ratio between the dose that you want between the energy released in the volume and the dose that is absorbed. Again, it's the same concept of the electron equilibrium. And with Cobalt 60, you reach value 1 for much smaller beams than for anything that you produce with a LINAC. So this is why we use Cobalt 60 in the Gamma Knife. And just to give some numbers, we have around 360 machines around the world, maybe some few more, and 2 million patients were treated with the machine. And how much cobalt? I already showed in the beginning. It's good to see it again. If 14 kilograms is how much cobalt is in a car, in an electric car, then in one Gamma Knife, you can think you have 20 grams. Now you multiply by 360 Gamma Knives around the world. Essentially, with one electric car, you could double the number of Gamma Knives that we have around the world. And I'm saying this because sometimes I get the question, oh, but cobalt in the Gamma Knife and so on. We are talking half of an electric car. It's as much as in one portable computer. And if you want to see some dimensions, here I took my telephone, which actually is an iPhone mini. So let's not get confused. It's a little smaller compared to a regular iPhone. And the actual pellets are in the photo on the right. And I have them with me. So when I turn off the slides and show you the camera, I can show it to you. And I want to, now the time starts to come towards the end. So I would like to conclude this presentation with a post that I found on LinkedIn by a neurosurgeon, Eduardo Lovo, who is using the Gamma Knife in El Salvador. And he says that when it comes to the Gamma Knife radiosurgery, one of the key advantages is the lower radiation dose to organs outside the brain. And he makes an example of treating a 5-year-old child for a non-cancerous condition. In that case, it's critical to minimize the dose outside the brain. And the use of low energy, relatively low energy, cobalt, compared to any energy you can produce with a LINAC, and the fact that you are distributing the sources on an array, and that you have the smallest lateral electron equilibrium, so reduce the dose to the brain, but also to the rest of the body due to lower scattering. And the three-dimensional dimension allows this to happen. So if you ask me what is my favorite application of Cobalt 60, I would say the Gamma Knife. But landing the Soyuz is pretty cool as well. And I just wanted to show you the 20 grams of cobalt that you have in a Gamma Knife. It's pretty neat, right? As much as in a portable computer.
Thank you so much indeed for spending time today to go through the use of Cobalt 60. I found it fascinating. I really did. I really enjoyed it. And thank you once again. So everyone else, if you remember to collect your CPD point, Charlene gave you the link. Thank you very much and goodbye.